We are live, February 12th of the day. Before I start, I want to readdress something at the end of yesterday. We're talking about representing Unicode in Python. There's a good tutorial on real Python about Unicode you guys can check out. Basically, what it says is Python is by default using Unicode, using UTF-8 encoding rules. And it can natively represent Unicode characters. I mean, if you see here, there are some of the examples I was trying yesterday. Like this is using like different types of encoding rules, but there's one thing that keep in mind, that some of the new emojis they are actually concatenation of multiple singular emojis, those simple emojis, and they put them together and they will display as a new emoji. But these are actually concatenation of old emojis, and they do not perform very well in Python. Like if we just write this out as actually, I can just show you very quickly. If we just say put this there, and it's actually going to decode it for you. So like what it actually is, there's a one emoji, like a linker, another emoji, another linker, another emoji. So this emoji is a concatenation of multiple elements, right? We can just say it that way. So I say if you do a len, it's actually 6, which means this emoji contains 6 different code. Why shouldn't code? There's 6 different Unicode. 6 different Unicode. Yeah, 1, 2, 3, 4, 5. Huh. I didn't really count it right. But anyway, you got the idea. Oh, I think it's no. It's these 2. Anyway, that's the idea. But I don't want to go to too much into details in this. It's actually quite confusing. I'm actually not quite understand why it's 6. When they actually show up, is this supposed to be 5? Anyway, that's not the point. The point is we're gonna go do today's LeetCode. Let's take a look. Nothing to worry here. Let's go. All right, we have been writing some easy and medium questions for a while. I'm starting to get worried that today we're gonna hit some difficult ones. Let's see. Number of steps to reduce a number to 0. This sounds familiar. Have I done this before? I have no clue. All right, a non-negative number. Return the number of steps, reduce it to 0. Okay? If then there's an even, divided by 2. Otherwise, you have to subtract 1 from it. Huh. I have encountered this rule somewhere in the past. Anyway, 14 is even, divided by 2. 7 is odd, divided by 1. 6 is even, divided by 2. 3 is odd. 8 is even, 4 is even. Oh. Yeah, this is an easy question. This is an easy question. And there's a hint. We just basically just keep doing it, because eventually you're gonna get back, you can get down to 0. Because you will eventually get down to 1. Right? So it's there's no trick, no nothing. Not sure if I'm feeling happy or not about this. I mean, if it's really simple, we might do another one today, just for the sake of it. Anyway, let's solve this one first. There might be a trick, but so far as I can see it, it didn't ask like how many, like the shortest. They just say the total number of steps. Oh, I think. All right, let's do it this way. What is screaming in my head right now is there is a mathematical solution to this, but we're gonna do it programmatically first and then do the mathematical one. So we say this is result, and while num, I'm gonna do if num is this, num minus equal 1, else num equal 2, then res plus equal 1, and then return the rest. All right, we might have some issues here because I don't really check for the edge cases, but we just run it. If all of them are missed by 1, then we just add 1 more. I mean, we can, I don't want to analyze it. Let's analyze it. So when the start with 0, I want to divide by 2. And wait, that's 1 step, 2 step, 3 step, that's 2. So we divide by, that's 3. Come up, that's 1. 4. Yeah, I think this is correct. I think this is correct. So we just run it. A number of steps. I just noticed this is 3, which is not correct. Oh, I have to change this to num. Yeah, this is correct. Alright, and we are going to simply put it in and then hit submit and it will succeed. Yep, and we done it. Give us some performance, mediocre performance. And now let's try to see if there's a math solution. If we can find a math solution through some tricks, then we don't do another one, right? So we just say straightforward solution. Just divide by 2 when it's even, and -1 when it's odd. Keep counting the steps. That is actually O log n because we actually divided by 2 every single time, and we hit 28 milliseconds, which gives us 85% ranking. All right, let's try to see if there's a math solution to this. What we do is just take out our paper. You know what I'm thinking? I'm thinking about binary. I am thinking about binary number. 8 is 1000, right? So basically we have 4. How about 14? What's 14? I actually don't know what is 14. Well, this is 8, right? 8 plus 4, so that's 14. 1110 is 14. Yeah, 1110 is 14. So okay, we have 4, but answer is 6, so that's now 4. So basically, it's the number, because every time we divide by 2 is we remove a 0, right? So we remove a 0, and then have to remove 1, turn 1 into 0, then remove, so it's 1, remove a 0, turn 1 into 0, remove another 0, so it's 1, 2, 3, 4, 5, 6. Yes. So we run a binary representation of the number, and if it's a binary representation, they will have a 1 at the front. So that 1 will be 1. That's the last of -1. And all the trailing zeros, they will be just, they will be 1s. So we just do a count. We'll do a count of how many 1s there are, except the first one, and then how many zeros there are. And all the 1s will be multiplied by 2, and all the zeros will be by itself. So here we have a second solution, which is more computer sciencey. So we do this. Does it have a? Does a Python string has a? Let's just do 14. What's a bin? 14? Yeah. So actually, I don't like it. That should be 2. I like it to be this. Okay. So a.count. Does it have? It has count. Oh. All right. It does have count. That makes things easier. Let's see if we can write in one line. So basically, what we need is bin nums, bin num, and we take this dot count. Oh, now we don't know the length. Can we know the length? I'm running on 3.9, so I want to try it again. Ha! I want to try it again, but it's actually not in the same statement. Alright, let's just do it this way. So this, I'm going to return bstr dot count 1. Actually, it's -1 because the front was always 1, -1 times 2 plus bstr.count 2 and plus 1. That's our solution. 2. It's not correct, man. Hold on. Why? I said count 2. My goodness. There ain't no 2. There's only 0. So this is the more computer sciencey solution. Submit it. Pass. Let's see. Oh, that's what the majority of people are doing. It should be the same. I don't know if it's the same. Actually not the same because you have to do count. A more computer sciencey solution. Leveraging, I like this word, leveraging binary representation of the given number. I don't know. What's the... It is log. Well, that's 8. Yeah, that's log. Well, converting is like log n. And then we have to do the count. Count is log n. So it's still log n. Still log n, but we hit a 32 milliseconds and the ranking is 63% ranking. Alright, now we're going to try to see if we can find a math solution to this. A math solution. Is it even possible to find a math solution? Even divided by 2, and then which means we just... What we're trying to do is to find... Oh, I cannot find. Just -1. Divide by 2 and a -1. Right? What does this do? So divide by 2. And divide by 2. It is constantly divided by 2. We're still doing it iteratively, right? We're trying to say, divided by 2. We can do log on it. And log 2 on it will be 3. Right, log. If we do log on 14 with base 2, we get 3. That means we can take, we can divide it by 2 3 times. And then the remaining is 6. Now let's check. I can't come up with a good math solution right now, but maybe other people have better ideas. Let's take a look. It's an easy question. I see it already. This is my first time. It is my first time doing it. What do people say? Counting number of 0 and 1s. Okay, that's our solution. 01. Huh? Huck? What language is this? Even though it's built in, doesn't mean it's 01. That's true. It's not 01. Oh, it's C++. It says it's C++. Oh, we can do -1 at the end. Ah, that is true. I can make it look much nicer. Alright, yeah, I can make it much long explanation, bit count, single line, bit count, one-liner. They have a one-liner here. Ah, yeah, that's just for one-liner. And I don't really like to do it because we have to compute it twice. But why is it -2? It shouldn't be -1. Yeah, it should be -1. Why is it -2? Oh, -2 because it didn't do. Okay, gotcha. Yeah, I don't like this. I like to. Oh, are you saying that we are making a little bit slower because we do this as well? Yeah, that's just micro, really micro. Let's say micro optimization is the worst enemy. It's just -1, so we know. Okay, so that's it for this one. Nothing to see. Do we want to keep looking for another one? Let's try another one. Let's try medium one. Can we random a medium one? How do we random? Pick one. Okay. What did they pick for us? Alright, let's do this. The first. Oh, it has not picked for. No, it's not the one I was looking for. I was looking for the first one that is. Yeah, let's try this one. This one will go somewhere else. Oh, I don't even have a place for this. Anyway, let's close this one. Let's add this to our GitHub account. And let me see. I think I have. Yeah, I have it. So what I need to do is. Oh, are these all have? Oh, they all do. Okay. Good. So we're gonna copy LeetCode 116 to LeetCode. Oh, I mess up the spelling. My goodness. It should be LeetCode with uppercase. And with this one as well. 1608. I don't even remember when I did those. Yeah, I need to put dates in it. I mean, the daily challenge is fine, but when we do the real thing, we need to put the not only the number 6665. All right, let's make sure we haven't done it before. No, we have not. 665. Okay. Alright. No idea what this one is. Could be hard, could be simple. Take a look. Solution is available. Alright. Given array nums with n integers, your task is to check if it could become a non-decreasing by modifying at most one element. We define an array as non-decreasing if, okay, zero-based, that is fine. So we can change 4 to 1, and this one we cannot. And then the fourth ON solution one time. Okay, so we want to see if it is possible to make it non-decreasing. That means only changing one and everybody else falls into place. Now, a non-decreasing array can be achieved by stack. So every time we push a number into stack, if the top of the stack is bigger than my current value, then we pop it out. Right? We pop it out, and then we can push it in. So we make sure that in the stack it's non-decreasing. So maybe we can do it this way. Given an array, right? We just do this, push into the stack, and we count how many numbers are popped out. That means how many numbers are not fitting into the original array. Because they say at most one element, right? At most one element. That means if it satisfies, then only one element shall be out of place. And if there are two elements out of place, right? If there are two elements that are out of place, then we cannot do it. So let's try this way. I'm not sure, but it's worth a shot unless we can find a counterexample that I'm currently thinking. So we're going to create a stack, regular, and for n in nums, if not stack or stack top is smaller or equal to n, stack dot put append. We're going to append n. Else, which means the stack is full and the top is larger, else, then we're gonna say stack is this, and what's else? Out of place. Right, we have out of place, so we say else out of place dot append stack dot pop. Now we don't even need. We just need a count. Just say count. We count how many are out of place. So we say stack dot pop and count plus equals 1. And we can do another check. If count is 2, and we just return false. Otherwise return true. So kind of stop it early. And then we can run the, these are very simple test cases. I think they all pass. We need to create more test cases. This is true. And this is 421, right? 421 is false. Nums, oh, that's a special array. Try possibilities. What the hell? Alright, pop. And then a pop isn't equal to 2. Is not equal to 2. Oh, hold on. Hold on. So initial is nothing. If not stack, I push it in, and then count is not the 2, right? And then we go back 2. Now we're going to push 2 into, because top of the stack is not smaller, it's bigger. So we pop it out. Oh, we forgot to, oh man, we forgot to, so the pop, are we always going to append? Ah, I know. If not stack and stack is larger than, then we do stack pop. Yeah, we kind of mess around the order. We do stack pop, and then we do count plus, and then we always going to append to the stack, no matter what. And then dash, man. What is this? It says list out of range. How is this list out of range? If not stack. And oh, if stack. My God, if stack. Yeah. All right, let's give it a shot. Let's give it a shot. Yeah, we don't even have to check it here. Just check it here. That's fine. Okay. So let's see if it works. Wrong answer. It's not. I didn't see it. I didn't see it. I haven't seen it. Okay, that's not correct. There are counterexamples. All right, let's try to see if we can find a counterexample. Let's see, counterexample, which means there are two things are out of place, but we can still make it work. How is that possible if two things are out of place? Yep, no, I did not see the solution. Okay, two out of place. Let's see. Let's give 1, 2, 3, right? And then 1, 2, 3, 4. Let's get a little bit more. And let's put two things out of place. Two things out of place. It could be two things out of place, and then we didn't detect it. For example, if we have the last number is small, no, it's still gonna be detected. Oh, I know, like this. 1, 2, 3, 1. 1, 2, 3, 1. And then we say this one shall be true, but I will return false. 1, 2, 3, 1 is 1, 2, 3, and this one actually should be false. Like this one, I shall be actually wrong because I did not do enough. Okay, yeah, I think I made a lot of mistakes. A lot of I want to find the error that's first. Yeah, I think I can find it very easy. So like 1. Pop once. Yeah, like this. I know. Like 4, 3, 1, 2, 3. Now this one, no, not 4, 3, 1, 2, 3. 4, 5, 1, 2, 3. This one shall be false, but I will say it's true. Yep. Let's try it. 4, 3, 4, 5, 1, 2, 3. And I will say it's true, but actually it's false. Yep, I was wrong. The reason is because this has to be a while loop. This has to be a while loop. But then if it's a while loop, we have another problem that this one will fail. Yep, and then we can actually try 1, 2, 3, and 1, and run the code. This one will fail. Oh, I haven't done it yet. So instead of if, it's a while. be a while loop, and this one will fail. Yep, it's because we see 1 and then we just pop everybody out, right? So what I think is, after we pop everybody out, that's the only situation that we have, right? So if we pop everybody out, and we know that everybody in front is, they're all in order, right? So we have one that is not in order. So what we do is, instead of a count, we're going to say stack, other stack, others. Right. So I'm going to push into the others, and then we're going to check eventually as long as we have one, either stack or others, one of them is empty or has only one value, then we are good. So we're going to say stack.pop. Instead of doing that, we're going to say others.append stack.pop. No, we don't have to do any of this. Stack with this, and we're going to return stack, len stack is smaller or equal to 1, or len others is smaller or equal to 1. One of them is true, and then we're good. Oh my goodness, this is ridiculous. I passed 2, but I did not pass here, and then I return true. How? Oh, okay. So the ones, so the others, so okay. No. We're gonna return len others is smaller or equal to 1, right? That means the stack is good. Or it's just the same thing. It's len others is not, and then the stack has to be, or len stack has to be smaller or equal to 1. Isn't that the same thing? No, it's not the same thing, because the others, I mean, that's like the case, right? So we have stack is good and others is empty, and we have stack is 1 and others have just like this, right? We have 4 and then we pop it, so so like it's supposed to be false because we have 1 in stack and the others has basically 4 and 2, which is not correct, right? 4 and 2, because these are not in order. So how do we handle this situation? I mean, we can count, but after counting, so every time when we pop out, right? We pop out and then we pop out and then we get more than 2 and that's done. And then if we keep popping, and then eventually we'll pop everything. So when we pop everything out, right? When we pop out a lot, in one session. So we pop out. So the pop has it's different. Like if it's out of place, then it should be a single pop, right? If it's out of place, then it's a single pop. If we pop more than 1, that means the value that's out of place is the current one, right? Think about it. We determine that the stack is in order, right? It's always non-descending. And if we go through nums, right? If we go through nums and we push it in, and we push it in, and we push it in, and then we find a new one that starts popping things out from the origin, right? Like this, we pop out. So like 1 push in, we pop out 2, and then we're done. Then 1 is this and the other. So when we pop things out, so we pop out. So we pop out 5. So we push 5 in, and then we pop out 4 and we push 4 in, which means at the end. We push 4, so pop out 4, and then pop out 2, and then push, and then pop out 4. So when we pop out everything, and then these shall be in a descending order. Hold on. If something is out of order, now we pop out once, right? And then we start going. So once we start the first pop, that's the first time that the original nums is not in order. Is that correct? Yes. The first time we pop, that means the original is not in order. And then we see how many we popped, right? We see how many we popped. If we pop only 1, and we can keep going, and then we pop another 1, right? If we pop 1, and we keep going, and then we pop another 1, that means those 2 are not consecutive, and then we just kill it. If we pop consecutive ones initially, and the consecutive ones themselves are sorted, right? And then the ideal is after we do this, we need to see how many are remaining. So if we pop consecutive ones, so we need to count every time we pop how many we actually pop. If we pop 1, we just keep going, and if it accumulates to 2, and then we cut it. If we pop is consecutive, we pop a lot, and then we need to see if the remaining is 1. If the remaining is larger than 1, then we have a trouble. I'm gonna go with this, and I'm actually using this. I think it's still a count. I think a count can work. All right, let's see. So basically we do this, right? And then the count is not going to be here. We're going to count every time when we pop. So we're going to put count here, right? So every time we're going to count. And we still need a total count. Total count is 0, right? So, I actually don't need total count. We just need a flag, right? We need a flag. Out of place, shown will be false, right? So we do count, and then we'll pop and plus 1 plus 1 plus 1, and then this we're gonna check if count equals 1 and not out of place shown, then we say out of place shown is true. Aleph out of place shown, already shown. Aleph count, so it's going to be count equals 1, and then we're going to say if out of place shown, now we turn into true, else we're going to return false. So out of place already shown, and we do another one, right? And else, so count is not 1, count is more than 1, then we're going to say, we're going to try to see how many remains, right? Because we know the ones we pop out, they are in order, so we need to see the remaining. If we're more than one remaining, then it's also a bad. So we just say else if the remaining is len nums minus count. If that is larger than 1, then we also return false. Otherwise, we'll keep moving. That is not correct. Huh. Why is that? Let's see the first one. First one should be true, but I say false. Okay, let's see. Well, stack, nothing, so count, not. Aleph, oh. If count, Aleph, count larger than 1 and that's still not right. Anyway, so initial count is 0, and then the first one is not going to go in. And the count is nothing, so we're append 4. So now stack has 4. Second one 2, while stack and the stack is larger, pop and count plus 1. Count is now 1. Count equals to 1. Shown is not shown, so if not. Okay, fix this. Now this is still not true. I say return false. It's actually true. How? So we go count is 0, nothing, nothing. So we go 1, 2, 3. Now the last one coming in, count is 0. I'll stack is larger, and then I think it probably should be larger than equal, right? No, it should be larger than equal. Why do we do larger than equal? Because I want to get all of these out. All of these out. But then we have an issue of if we want to get all of these out, then like 2, 2, 2, 2, right? And then they're gonna get popped out. So you can't get all of these out. All right. So the only scenario, right? The only scenario that we have can make things complicated is when. So when they all pop out, it's fine. And then we have a 1. That means we're going to pop out as 2, 3, and the remaining is 1, 1. Is that the only scenario, right? That's the only scenario that can mess us up. Otherwise, the count by 2 does work. Count by 2 does work except for this. So what we can do is, yeah, let's, I think that's the only case, right? That's the only case. Because the last one, it doesn't really matter. We can always change the last one. The last one is free. So which means if the front, everything in the front has less than 1, and then the last one definitely works. If the front has already 1, like well, I already have to change 1, and when you see the last one Hold on, let me think. Let me think. If the front we can actually see, right? We can actually see if it fits into the yeah. I think we can just consider the last one as the odd one out. So we do this and we know that this one will fail. That's fine. So what we do is instead of go to the end, we go to not to the end. So I'm going to say for I in range, I'm going to go from 0 to len -1. And then num here. All right. So we do all this. Pop and then we count. If already 2, then we and then we end it. If it's not 2, right, at the end, right, at the end. Now we're gonna check. If we can at the end, so we need to count as smaller or equal to 1, right, and then we say if nums, the last one, is larger or equal to the last of the stack, then okay, so it'd be like this. If count is 1 and num this is smaller, that means we need to change 2. Then now we're going to return false. Otherwise, we're going to return true. Num I. So these all pass. Ooh, I'm not quite sure. Honestly, not quite sure if this works. I suddenly think, okay, let's try this. If it's still not working, we're gonna try to figure something else out. Let's try. Let's see. No, it's not right. I don't think that's the solution. I still didn't see it, but I guess it's not correct. Okay, so this still doesn't work. I mean, we're kind of just trying to hack it. All right, let's try moving window, sliding window on this. So if we do a sliding window, then we have a front and an end, right? We have a front and an end, and then the end will keep moving forward if the current is I'm going to think the length. So the end will move forward if so we have a front, like a front pointing here, end pointing here, and then if the end is larger than the front, we'll keep moving this, right? And then moving this, and then this one is not larger to this, and then they are far apart. Wait, how? So what we're saying is we try to make the sliding window is increasing, like strictly increasing, and then we will encounter a one that is not. So yeah, we just go to here, and then we compare to the front, then this one is not, right? Then we move the front down to this one. So we're gonna start again. How is this helping? How is this helping? How is this helping? What's the end result we're looking for? We're looking for changing at most one number, right? At most one number, so it will become strictly increasing. So we just go through it, and then strictly increasing. I still want to go for the popping. I think the sliding window might not actually work. If we still go through the popping idea and we check the results of the pop, right? So if we go 4, 2, 3, and then we pop, we're gonna pop 4, and then pop will be 2, and then that's it. So we have 2, 3, and the other one has 4. That's 2, 3 is the original, 4 is the pop out, and we know the original is all good. 4, and then we say that's good, right? If it's 4, 2, 1, we're gonna say 4 is gonna pop out, and then 2 is gonna pop out. It's gonna be 1 and 4, 2, and then 4, 2 is not increasing, not strict increasing, so this one is also bad. So basically, what we're trying to say is, if we pop, right? If we pop, and after we pop, the out of place contains only one element, or it's empty, then it's a good case. If the outer element, like for this case, the out of place element is going to be 1, 2, 3. That's also sorted. Then basically the 2 rows they just swap. That's also good. Well, it's actually no, because what you're going to do is become 1, 1 and 2, 3. Right? It's 1, 1 and 2, 3. How do we reason 1, 1 and 2, 3? Because it's fine if we do this, then we have like say 2, 2, 2, 2, and we're just gonna keep popping out, and then we have 2 and a bunch of 2s, and that is still considered good. So we're gonna pop when it's larger or equal to. Yeah, if it's larger or equal to, just keep popping, keep popping, keep popping. Then that means what's remaining on the stack is a strictly increasing. But what is this going to do to something like one, like a bunch of 2s, and then we have 3 at the end, and then there's 2, which is keep popping, and eventually one is going to be 2, 3, the other can have all the 2s, 3 2s. How are we going to rationalize this? How do we know that this is okay? Well, these are out of place, right? And they're out of place when they popping out. They follow the original. They follow the original order. And if we don't pop, right? If we don't pop, then we're gonna end up with this situation, the 1, 2, 3, 1 situation. We're gonna end up with 1, 1, 2, 3. And I just how do we rationalize 1, 1 and 2, 3? What does 1, 1, 2, 3 means is we have some value in it, and then we pop 1 out, and a 2, 3 is good. 2, 3 is sorted. 2, 3 is sorted, and the remaining is also good. Does that mean it's good? Like as long as the ones gets popped out are good, are sorted, and then it doesn't matter how many is remaining inside the original stack, because when that happens, right? If you think about it, the original stack, and then we keep pop, 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 and until we stop, is because we hit a number of the same size. So we just pop everything in the middle out. Is that considered to be good? Well, I don't really think so, because if we have, say, 1 and 2, right? If we have 1, 2, 3, 1, 2, 1, 2, 3, 1, 2 shall be a false. 1, 2, 3, 1, 2 is a false. 1, 2, 3, 1, 2 is a false. The pop, 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 and then we have 1, 1, 2 on one side, and then we have 2, 3 on the other side. Yeah, and then that's the other situation, right? We have a different situation. All right, let's keep thinking. If we compare just like neighbors, I still think this shall work. What if we try to find the smallest value? The smallest value has to be somewhere, right? Somewhere. And if we say we change at most one element, okay, so if the entire thing is sorted, then that's fine, right? If it's not, that means there are outliers in it. And this outlier, we should only have one outlier. So what's going to happen if we have one outlier in it? That one will stick out, which means if we can just go through the whole thing one by one, one by one, one by one, and we find one that is odd, right? Which means one is odd, it means to stick out. It is larger than the one following it. And we note down, right? We note down we have one. And then we just keep going, and then we note down all the odd ones out. So like in this case, we will notice 3 is the odd one, right? We notice 3 is the odd one. But in fact, it's not 3, it's 1 is the odd one. Oh, man. Can try every one of it, and then okay, that's actually a possible solution. We try every one of it, try 4, right? And then we see it's the first one, and then we try it to 1. How do we know that it's good? Right, this is O(n) squared, it's not going to work. It's not going to work, so we cannot try that. We have, like, we pop. Yeah, the problem is just when we pop things out, some of this will result in very weird scenarios. Right, this will result in the original be 1, 1, 2, and the additional will be 2, 3. And based on our rules, if it's a 1, 1, 2, and 2, 3, we say it's bad because the thing that's not in it is more than 1, and then we say no, we don't like it. But if we do 1, 2, 3, 1, and we pop out the remaining is 1, 1, and 2, 3. Like, how do we reason this? Is resulting in 1, 1, and 2, 3. And now we're saying that if that happens, all right, I'm gonna cheat a little bit. I want to see the error cases that we have. You ready? All right, so this is the one that we got wrong, 5718, which is false, but we say is true because 5, 7. How is that true? Oh no, wait. Expected is true. Output is false. Oh, 1 could be turned to 7. Yeah, 1. We hit 1, and then we pop 5, 7 out. And then we have 1, 8, and a 5, 7. Huh. Okay. This one is false. So this one's false is because the one that the odd one out cannot. So like we change the odd one out does not make it work. Does that mean we just search through? Yeah, let's put this one in. This is a good test case. Actually, I'm going to put both in. I'm lowering the difficulty of this because I'm checking the test case. This one should be true. And 1, 2, 3, 1, 2 is false. Oh, this is taking way longer than I had expected. Alright, let's focus. Let's focus. I feel like we're at the edge, but we just couldn't really figure it out. So what if we just check adjacent, right? So adjacent, what we expect is everything is good. And if it's bad, then we're going to find the odd, right? The one that's larger than the following. Now, when we find one that's larger than the following, there are two situations. One is the larger one is the culprit, which will happen if the following and the one before the large one is in line. Now we know this one is odd, and then we can change it. Or it could be like this. It's this one is odd, and the one that's smaller than the previous one is odd. And when that happens, how do we know that is? So we say that if this bigger one is, then we just compare these two, right? So these two. If this is larger than this, then we say this one is odd. And if this one is odd, is when we compare these two, they don't fall in line. So we say this one is odd. Then we're going to compare these two. So if these two follow, then we change this, and then we keep count. We change this into some value in between, right? And then we can keep count. So that's like a good scenario. Now the bad scenario is like for this, we know that these two don't match. These two don't match, so this one must be correct. Let's just say this one must be correct. And then we check these two. Now these two also don't match. And then we're gone. Right? Then we're gone. Maybe this one will work. Maybe this one will work. So we're trying to, like, when we find a pair of adjacent that does not follow, then we try to make it work. Right? We try to make it work. And if we did make it work, we move on, but we keep track. We already made one work. If there's another one, then it's a goner. And if we cannot even make it work, then it's a goner. Now let's try it. Let's try it. Let's try this solution. So it's a very different solution. So we're gonna just say if len nums, okay, that's for I in range. So we're gonna do, because we're gonna check the next one. So it's gonna be due to len nums -1, right? And we're gonna check j will equal I plus 1. If nums I is larger than nums j, then that we have a crisis, Now to check the crisis, we're going to say check whether nums I is odd 1. So how do we check? We check if nums if I equals 0, or right, that's the odd one out. Either this is the first one, or nums I minus 1 is smaller or equal. Yeah, that's fine. Smaller or equal to nums j. Right. So if so they are in line, then we can change what I'm afraid is like we're disagree. Like every time we find an odd one out, then we make change, which should be right. Which should be because we can only allow for one change. If we find something that's odd, then we should change it, and then we find another one, then we're done. Because if it's correct, we should only do it once, right? So if this nums I, we actually make a change to it, equals, we can actually just make up a number that doesn't really matter which number. Let's just make it nums j, right? We make a number, and we say num change equals 0, and then we just keep count. Num change equals 1. All right, that's one situation. Elif. So this is where the front is wrong. Now we can be the second one is wrong. Right now we can be the second one is wrong. Now the second one is wrong is when the front, the second one is the odd one out, is when the front one, my current one, Elif j is equal to len nums minus 1. So j is the last element, or j is the last element, or nums I is smaller or equal to nums j plus 1. So that is when j is the odd one out. So I'm actually going to put this here. I'm going to say check whether nums j is odd 1. Right, num j could be the odd one. So if it's the odd one, then we make nums j equal to nums j plus 1, right? Oh, there's no nums j plus 1, so we can do nums I. Num j equal to num I, because it's fine, which means like we turn this into 3. All right, so these two, and then num change plus equals 1. Else, which means neither situation work, like in this scenario, then we're just gonna return false, because it's incompatible to make one change, right? This is when this happens, when nums I is larger than nums j, right? And we do this, and then when it's n, we're gonna check if num change equals 2. So we have 2 changes. We also return false. And when all is done, we're gonna return true. All right, let's try this. We pass all test cases. All right, we're gonna try this one. I don't want to see. Let's just try it. Submit. Got it. Oh, we ran through some difficult. This one took like what? This was pretty fast, about an hour. About less than an hour. So we are 1 hour 10 minutes in. I think I started working on this around maybe 14 minutes. So about 45 minutes to solve this. Oh my god! And we have actually pretty good time. A pretty good time. Yeah, we have 97%. So apparently this one is correct. Okay. Let's go. This is not straightforward. I've been writing like straightforward solution all the time. This is not straightforward. My straightforward. Did you spell it wrong? Straightforward. Come on. My straightforward ideal is to use stack and pop the odd ones out. Now it does not work because it is hard to determine whether it's hard to determine because it's hard to reason with the test case 1, 2, 3, 1. If we pop odd one out, the final result will be stack equals 1, 1, and odd ones equals 2, 3. It's just impossible to tell whether this is a good state, whether it is good or not. The changed solution does not use stack at all. It checks adjacent values, adjacent numbers, and determine and numbers. Whenever an odd one is discovered, that is, the current value is larger than the next one. So when that happens, the current value is larger than the next one, then whenever this is recovered, we need to make a decision whether the odd one is the current value or the next value. We can make this decision by checking the numbers surrounding the suspicious one. For instance, let's say we find that nums I is larger than nums I plus 1. If nums I is the odd one, then we must have nums I minus 1, nums I minus 1 smaller than nums I plus 1, or if nums I is the first value of the first value. Similarly, if nums I plus 1 is the odd one, then we must have nums I smaller than nums, smaller or equal to nums I plus 2, or if nums I plus 1 is the last value. If the above condition is met, then we have found an odd one that can be modified to maintain the increasing requirement. If neither of the above condition is met, then we already have a wrong, and we already cannot, then we already have a false situation. We already have a false result. We can continue this process and keep count of the number of changes. Once the number of changes becomes 2, we have a false result. This is go on, and we run at 172 milliseconds, which is 97% of the ranking. All right, pretty good. Let's go take a look at the solution. Brute force. Yeah, not even gonna check brute force. For each possible, checking the sequence of monotone increase. Yeah, I'm not gonna do this. Reduce to smaller problem. Okay. Locate and analyze problem index. So this one is ON. This one is also ON. This is more of a specialized riddle than a program problem. Huh. I don't even know what specialized puzzle is. Why are you not showing me? I'm gonna refresh this page. Alright, so we're gonna just not dealing with the brute force. Let's see approach 2. Reduce to a smaller problem. Then we may remove A0 without changing the answer. Similarly, now we may remove this without changing the answer. Then after these removals, very few numbers will remain. Consider the interval ij corresponding to the subarray. We know we do not need to modify AI, and we can consider solving a problem with the interval. Okay, is there recursion? I don't think it's recursion. If the interval has size plus, then we did not find any problem. With the length of the interval under consideration being this. Has 5 or more elements, then there are 2 disjoint problems that cannot be fixed with the run replacement. It's now at most 4 elements, which we can easily brute force. Oh wait, what? Huh? It's reducing the problem space down to. So we're shrinking from both sides, and what we're saying is if we have 5 or more, then it's unsolvable, because if we have 5 or more, that means we have two increasing subsequence in the front and the back, and we have another one in the middle. And we say this is not solvable because that one, okay, if that one belongs to the front, then the back is bad. If that one belongs to the back, then the front is bad. If that one does not belong to anyone, it's like in the middle, then it is going to be bad, no matter what. Okay, that makes sense. Yeah, that makes sense. If it's 5 or more, then it's bad. If it's 4, I say if it's 2 or less, then it's good. Yes, 2 or less, then it's good. If it's 4, then we just need to double check on it. Okay, but what the hell? You have to rerun the brute force? All right, let's see the last one. The brute force is 01. I know. It's the last one. Ooh. Looks simple. So we go from if AI is larger than, okay, that's my case. I mean, yeah, I don't really need this one. I don't even need J. That's true. If P is not none or then false, and P equals I, then we say I is the odd one out. Now, at least there's one odd one. And then we keep going. If we have found it again, then we say it's bad. Otherwise, return P is none. Okay, or P equal to 0, it's the front one out. P equals is the one before the last one, or wait, what the heck? If there is 0, the answer is true. If there are 2 or more, the answer is false. As more than one element need to be changed. In the problem index P, we only care about the surrounding elements. Thus, immediately the problem is reduced to a very small size and can be analyzed by casework. And then we can make the array good by changing a P equals, that's good. If P equals this, then we can make the array good by setting P plus 1 equals a P. I would say P is the one that's larger than the final one. And we can change AP. This one, okay, got it, yes. Otherwise, they all exist, and we could change AP to be between. Okay, or we could change this to be between. Oh, this is the same idea as mine. It's just expressed in a little bit different way. Yeah, we don't need to do this. Okay, we hit this. This is exactly the same idea, but implemented using a slightly different way, like analysis at the end. Again, this is the same. This is the exact same thing as this. I mean, I just need to change this. So instead of saying j, I put all the j into n plus 1, right? And then j is n plus 1. And j is n plus 1, which is reducing the number of symbols. And then we say n plus 1, so not n plus 1. Oh, come on, it's I plus 1. I plus 1, and this is just I equals minus 2. That's I plus 1. Or this is I plus 2. And then we change I plus 2. Yeah, and this still shall work. And I change this to I. What else? Out of space. Oh, I don't think this is if I is last one. Oh, it's plus 1. Yeah, that still works. It's the same if you take a look, right? The condition is 0 here, minus 2, or this one smaller than this, or this one smaller. Yeah, this is the same thing. And I would say if the change equals 2, which is this. All right, we got this. We got this. We got this. Easiest Python solution. Nah, when are you gonna do this? I don't like it. All right, that's it. That's it for today. We effectively solved 2 problems, and this is a little bit trouble at the beginning, but I am very happy that eventually we got it done. All right, that's it for today, and I'll see you guys tomorrow. Adios.